Good evening, Lamai. Right, today we are going to discuss about the metallic bond. Right, today our topic is metallic bond. Right, so this is actually the third kind of primary bond we are studying. Right, so basically with our lesson, right, there are two kinds of major bond types, no? The primary bonds and the secondary bonds. Right, and then when it comes to primary bonds, we have three types: covalent bonds, ionic bonds, and the metallic bonds. So we have done the discussion about the covalent and the ionic stuff. Right now, today we are going to discuss about the metallic bond. Right, this is the third type of primary bond we are discussing. Third and the last type. Right. Okay, metallic bond. Yes, before starting the discussion about the metallic bond, right, first discuss a bit about the metals, how they behave, right, knowing that the nature of metals will be helpful for you to clearly understand the metallic bonding situation, right? So metals, when it comes to metals, right, normally the metals are situated at the left hand side, normally the left hand side of the periodic table, right? When going to the right, the atomic radius will decrease, right? But when it comes to metals, normally metals are with the largest atomic radii of elements in your period, right? So if you are to take think of some example, let's take the third period, the third row. If you take the third row, the sodium, magnesium, aluminium, right, silicon, phosphorus. That is how the things vary. No? So these are considered as the metals. No? These are the metals in your third row. No? So basically, when considering a row of elements, period of elements, so basic metals are with the largest atomic radii, right? So that their outer electrons are bit away from the nucleus compared to the other atoms, right? When it comes to metals, their outer electrons are bit away from their nuclei, right? Compared to the other atoms, right? On the other hand, right? When it comes to metals, those are situated, right, directly after the. So those are situated in your periodic table directly after the, just after the noble gases. So if you are thinking of the electronic configurations of these things, so sodium's configuration is neon and 3s1. When it comes to magnesium, it is neon and 3s2. For the aluminum, it is neon and 3s2, 3p1, right? Just after the noble gas, you will find the metals in your periodic table, right? So first thing I had tell you is that metals are with somewhat larger radii compared to other atoms of the periodic table. Secondly, what I have said is those metals can be found just after the noble gas, in your periods, right? So both of those facts ultimately leads metals to release their outermost electrons easily than the other elements, right? So that by releasing the outermost electron here or a few of the outermost electrons here, right, metals are able to come up with the most stable electronic configuration. On the other hand, as those guys are with some greater radii, or the valence electrons are away from the nucleus, those are very easy to release. So both of these effects, because of both of these effects, metals tends to release their outermost electrons easily compared to other atoms, right? So that when it comes to metallic lattice or lattice, the solid structure of metal, right? Metals appears like this. So metals will easily release their outermost electrons, right? Ultimately, you will find some kind of a picture like this. So these are the metal atoms, right? So metals tends to release their electrons easily, right? So after releasing the electrons, right, metals will come up as positive atoms. They will come up as positive ions. Then so released electrons will be in the vicinity of these ions, right? This kind of a structure is possible with metals, right? So metals will release their outermost electrons easily, and so those released electrons won't go far away from the metal ions, because those will again tends to attract towards the cations, so that metals are ultimately with this kind of a lattice structure, where you are with positive cations of the metals dipped in a sea of electrons released by them. Metal cations are dipped in a sea of electrons actually released by the metal atoms when forming the cations. So this is the nature of a metallic lattice. This is the nature of a metallic lattice. So you would see the sea of electrons appearing like this, electron sea. So metal cations are dipped in a sea of electrons. That is how a metallic lattice is formed, right? So now let's discuss about the metallic bonding. Metallic bonding, right? So the idea is this. So when we are to think of a bond means a method of connecting masses. I have given you this idea, right, when we are discussing about the covalent as well as the ionic bonds, right? So bond means a method of connecting masses, right? So when it comes to metal, these are the masses. Basically, electrons carries a kind of negligible mass, lamai. So the mass of electron is negligible compared to the mass of a proton, right? So electron mass could be neglected, can be neglected. So the masses of this lattice is these guys. These are the masses, right? So way of connecting masses is referred to as a bond. Then the metallic bond is actually way of another method of connecting these masses together, right? Actually, how these masses are connected? One may think as these masses are positively charged, they should repel. The opposite charge, the similar charges should repel. So, but these masses are connected via a bond called metallic bond. These masses are connected via a bond called metallic bond. Let's discuss how that bond is created. It is like this, Laman. So, as these positive charges, as these masses, the ions are positively charged, those ions will attract heavily to the sea of electrons. Those ions will attract heavily to the sea of electrons, because the sea of electrons, right, is with some greater negative nature. More of the electrons are released to the sea, electronic sea, right? So the sea of electrons is with some greater negative nature. So these positive masses, the positive ions, cations, metal cations will attract to that sea of electrons. Even this one, all of these cations will attract to the sea of electrons. So then what will happen? So that these cations will be bound with the use of sea of electrons. So that is what we refer to as the metallic bond, right? The metal cations are attracted to the sea of electrons, right? This is what we are referred to as the metallic bond, right? This is the metallic bond. Attraction of positive charges or attraction of metal cations to the sea of electrons is referred to as the metallic bond. Actually, this is like a multi-bond. The sea of electrons is like a multi-bond. So you may have come across this idea, right? So basically, with a multi-bond, let's think of sticking your shoes, right? If it is broken, right? You may have used that multi-bond kind of a rubber glue, no? Right, to stick the things together. So then what will happen? So basically, see how you are supposed to connect the two masses with a multi-bond, right? So what you are doing is just paste some multi-bond layer here, and then you put the other mass on top of that, right? So that the multi-bond will appear, right? The rubber glue will appear between the two masses. The two masses are connected to the rubber glue, while the glue will be appeared between them, right? That is how the masses are connected via a rubber glue, right? Like multi-bond, right? So that is the same, the idea is the same here, right? The two masses are connected via a glue like sea of electrons, right? So it's just like a rubber glue. Both the masses are connected to that thing, so that will stick together, right? So that is the idea. That is how a metallic bond is formed, right? So this kind of a model is first proposed by two scientists referred to as known as Drude and Lawrence. So that this model is referred to as the Drude-Lawrence model, right? This is referred to as the Drude-Lawrence model, right? Drude-Lawrence model. Drude-Lawrence model, right? This is for the metallic bonding, right? Drude-Lawrence model of metallic bonding. Right now, this is the idea, right? So you can go through the note. It is said like this at the first 2 points, right? Valence electrons in metal atoms are loosely bound, and therefore metal atoms tends to, right, release electrons and form positive cations easily, right? So then it says metal cation. So then it says about something about the Drude-Lawrence model. It says metal cations are embedded in a sea of electrons which were given off by metal atoms, and the electrostatic attraction between positive cations and the electron sea make the metallic bond, right? So you can mark this, right? So you have the electron sea here and the positive cations, right? So you have the positive cations and the electron sea appearing here, right? So these are the cations, metal cations, right? And this is the electron sea. This is how the metallic bonding is formed, right? Okay, let's discuss about the factors affecting the strength of this metallic bond. Let's discuss about the factors affecting the strength of this metallic bond, right? The idea is this, right? The strength of the metallic bond, right? So there are three factors. We'll discuss about three factors which will affect the strength of the metallic bond, right? Three factors. Yeah. The first thing is actually charge of the cation. Is the charge of the cation, which is also can be referred to as the number of electrons released to the electron sea, right? So let's come up with that idea. So number of electrons released to electron sea. One can say, think of this as the charge of the cation as well, right? Charge of the cation as well. Both are same. Charge of cations, right? So if you are to release one electron to the electron sea, your charge will be +1. If you release two electrons to the electron sea, charge will be +2. If you are releasing three electrons to the electron sea, that means your atom will convert to a +3 charge. Releasing three electrons from your neutral atom means it is producing a +3 charge, like that. So number of electrons released to the electron sea is actually something about the charge of the cation, right? So what will happen? When the number of electrons released to electron sea is high, then the strength of the negative charge, the strength of this rubber glue is high. When you have released more number of electrons to the electron sea, that means the strength of the electron sea is high. The strength of the electron sea is high, so that these positive ions will greatly attract towards that negative sea, right? Sea of electrons, so that the metallic bonding will be stronger in such a situation, right? When you are releasing more electrons to electron sea, the strength of the electron sea will be high. That means positive metal ions will attract heavily to the electron sea, which makes them stick more stronger than the other instances, right? So the metallic bonding strength will be high when the number of electrons related to electron C is high, right? Okay, that is the idea. So when this is high, your metallic bonding strength will be high, right? Metallic bonding strength will be high. The second factor which affect the metallic bonding strength, the second factor affect the metallic bonding strength is the radius or the size of the metal cations. Radius or the size, both are the same. Greater the radius means greater the size of metal cations. Radius or the size of metal cations, right? So it's like this. So let's compare two situations, two guys here, right? Let's discuss about two guys. Let's compare the lithium and the sodium. So when it comes to lithium and the sodium, right? Lithium produce the +1 charge ions, and sodium as well produces the +1 charge ions, right? But both are releasing one electron, C. But when it comes to size, sodium plus is larger than the lithium plus. Sodium plus is larger than the lithium plus, right? Why is that? Because sodium plus carrying 2 electronic shells, while the lithium plus carrying only 1 electronic shell, right? So when the size is larger, one can say the charge density or the charge strength is smaller, right? The charge density or the charge strength is smaller, right? So with this guy, the Q plus over R plus or the charge density is high, and for this one, the charge density is low, right? So charge density will be low when the R is high. When the R is high, this ratio will be low. When the R is low, this ratio will be high, right? So charge density means the charge strength. If you have the same amount of charge with a very small space, that means the charge is more concentrated. That means, right, its charge strength, the positive charge strength is high, right? If the same charge is with a larger volume, that means charge is diluted, right? More dispersed, right? So that means their charge strength is low then. So when you are with a lower radius, that means your charge density is high, that means your charge strength is high, that means those things will greatly stick to the negatively charged electron C, right? If you are with a lower radius, that means your charge density is high, your charge strength is high, that means those cations will stick more strongly to the right negatively charged electron C than a cation with larger radius, right? So that is how the radius or the size of the cation affects to the metallic bonding strength, right? So if the radius of the cation or the radius or the size of metal cation is small, then your metallic bonding strength will be high. That means their charge density or the charge strength is high. That means those will strongly attract to the right negative charge electron C, right? That is the idea. So these facts will lead to a greater or stronger metallic bonding, right? These facts will lead to a stronger metallic bond. So metallic bonding strength will be high if these things happens like this. Metallic bonding strength will be high when you are with a smaller radius as well as with a when you are releasing greater number of electrons to electron C, right? Those are the major two facts affect to the metallic bonding strength. But when it comes to D block elements, right, another fact matters. When you are supposed to compare the D block guys, another fact matters. That is also referred to as the ionic nature. Ionic nature means it is all about the ionization energy of those atoms. When the ionization energy is low, when the ionization energy is low, that means the electrons are easy to release. Even with a lower energy, the electrons will be easily removed to the electron C. Electrons will be easily removed to the electron C if the ionization energy is low, right? That means the density of electron C or the charge of electron C will be high then, so that the cations will greatly attracted towards the electron C then. So the metallic bonding strength will be high there, right? So that is how the ionic nature or the ionization energy of the metal atoms affects the metallic bonding strength, right? So with these three facts, right, we can compare the metallic bonding strengths of metals, right? So when the number of electrons to electron C is high, when the radius of the metal cation is low, or when the ionic nature of your metal atoms is low, your metallic bonding strength would be high, right? That is the simple idea here, right? So these are the three facts affect to the metallic bonding strength, right? When you are supposed to compare two atoms, so you should compare these things with this order, right? It's like this. So if you have to compare the lithium and the sodium, both are releasing 1 electron each to electron C. So with this fact, you can't comment on the metallic bonding strength of sodium and lithium. But when it comes to radius of the metal cation, yes, the radius is smaller with lithium, so that it should have the greater metallic bonding strength, like that, right? In order, you have to consider these facts, right? Okay, when you are supposed to compare two metals, with the two, which one is with the greater metallic bonding and which one is stronger metallic bonding, right? Okay, that is the idea. So these things are normally written in note, right? So actually this ionic nature will be considered only with the D block guys, right? D block guys. There's no effect of the ionic nature with the S block guys, because when it comes to S blocks, always they release the outermost electrons completely. So the group one atoms, right, always release their outermost one electron, that just electron that will be released always to the electron C. When it comes to group 2 guys, group 2 metals, right, so all of those will release both the 2 electrons to the electron C. No worries there, right? Always those will release to the electron C. But when it comes, why is that? One can ask why is so? Why is the group 1 guys release that electron, and why the group 2 guys release both the electrons? Why do they are not stop at releasing only one electron? The reason is this. The reason is, by releasing 2 electrons, the group 2s can achieve the noble gas configuration, right? So that definitely the 2 2s will release both of their outermost electrons to the electron C. When it comes to group 1s, definitely it will release, those will release the existing electrons at the outermost shell, the 1 electron there, right? But when it comes to D block elements, let's consider some 2 D block elements. See, when considering D block guys, the thing is a bit strange, right? Situation is a bit strange with the D block guys. That is where you need to know about this ionic nature. It is where you need to concern about the ionic nature when it comes to D block guys, right? So this thing is only about the D block elements. We need to compare this, consider this, right? So it's like this. So when it comes to D block elements, see, so consider the iron stuff and the zinc and iron. See, so zinc D block guys, right? Zinc is with argon configuration and, right, 4s2 3d10, right? But iron is with the 26th, this is the 30th, is with argon configuration and 4s2 3d6. Here is 4s2 and 3d10. So here, by releasing 1 or 2 electrons, these guys can't achieve the noble gas configuration. By releasing 1 or 2 electrons, a few electrons, you can't achieve the noble gas configuration. So you have to release 12 electrons here, you have to release 8 electrons here to achieve the early noble gas configuration. So that, right, when it comes to d block elements, those are not going to release all the outer electrons. Those are not going to release all the outer electrons to the electrons. That can't be done. No, you can release 1, 2, 3, but you can't go beyond that, Lamai, because it is hard. No, when the electrons are released, the charge of the cation is high, so it is very hard when it is very hard to release electrons from a species with a greater positive charge, right? So that you can't release more than four electrons there to the C, right? So 3-4 electrons, that is the maximum, right? So when it comes to D block, guys, the ionic nature matters. That means the ionization energy matters. So when it comes to these guys, so you see this guy is with a completely filled. This guy is with a completely filled, right? Subshells. This guy is with a completely filled subshell. So stable configuration. Stable electronic configuration. Stable electronic configuration means your ionization energy will be high. So your ionization energy will be high. See, the ionization energy will be high. So this guy is not with such a stable configuration. So this is not a stable configuration. So not a stable configuration. So that your ionization energy will be low compared to the sink situation. So it is easier to release electrons from this configuration than this, so that this will form some stronger electron C, so that the metallic bonding strength of iron will be greater than the zinc. Metallic bonding strength of iron will be greater than zinc. That matters because of the ionic nature or the ionization energy varies, right? Okay, so to comment on the D block, guys, this effect is important, but not for the S block, guys. S block things can be compared with the use of only these two factors, right? That is what it says, right? So these things are there in your note, so you can have a quick note about zinc and iron if you need. Under the ionic nature, you can have a quick note about the zinc and iron, right? So ionic nature basically matters when you are to compare D block, guys, because all the D electrons, all the valence electrons can't be released when it comes to D block, guys. So you can't release such number of electrons, right? It is very hard to form such large cations, right? +4, +6, +7, +8 cations are not formed, right? So that the ionic nature matters there, or the ionization energy matters, right? Okay, those are the major three factors affecting the metallic bonding strength, right now. So let's discuss about the properties of metals. Let's discuss about the properties of metals with the use of this model. Let's discuss about the properties of metals, right? Okay. Right, physical properties of metals. Actually, physical properties of metals can be explained with the use of this model. With the use of this model, we can explain the physical properties, right, of metals, right? Let's use this model to explain them, few of them. Right? The first thing we are going to discuss is actually the electrical conductivity. What this means, Lamai? What this means? Electrical conductivity. Conductivity means moving charges from one place to another place. Right? Conductivity means that, no? The moving charges from one place to another place. So charge should be moved from one place to another place. that is what is referred to as the conductivity, right? To do so, right, there should be movable charges, moving charges, mobile charges. So in your material, mobile charges should be there to give you some electrical conductivity, right? Electrical conductivity means, right, moving the charge from one place to another place. It is a conductivity between two places, 2 points, right? So to do so, you should have mobile or the movable charges with your matter, right? So when it comes to metals, yes, you have movable charges. What are those? Those are the electrons. Electrons in your electron sea can be moved easily. It's a sea of electrons, right? So floating here and there, sea of electrons. So those are movable charges, moving charges, mobile charges. So mobile charge carriers are there. So if the mobile charge carriers are present, your material possesses some electrical conductivity, right? It's all about the mobile charge carriers, right? Electrical conductivity, right? So if mobile charge carriers, mobile or movable charge carriers are there in the material, such materials can show electrical conductivity. That is the idea. That is the idea, right? So in metals, you have mobile electrons as mobile charge carriers, moving electrons, movable electrons as mobile charge carriers. So metals can conduct electricity, right? So metals can conduct electricity as metals are with movable or mobile electrons, which is appearing with the electron C, right? Metals can conduct electricity. Idea is simple as that, right? Idea is simple as that. So metals are able to conduct electricity. We know that. We can explain that behavior, that physical property, right, with the use of this Drude-Lorentz model, right? The Drude-Lorentz model, you see the mobile, the sea of electrons, mobile charge carriers appearing. So that we can think of conductivity even with the use of this model, right? So if you were to apply some positive terminal and a negative terminal to these two things, right, then what will happen? Right, electrons will flow from here to here. These electrons will flow from here to here. Complete in circuit. Electrons will flow from here to here, right? Because electrons will be pumped by the negative terminal and electron will be attracted by the positive terminal, so that electrons will flow from here to here. As mobile charge carriers are there, these 2 points are actually acting as a right conductor. So this could be act as a conductor, conducting the electricity. That is how the thing is done, right now. Okay, so that is how we are supposed to explain the electrical conductivity with the use of this model. Electrical conductivity of metals with the use of this model, right now. Okay, right. Then let's discuss about the thermal conductivity. You clearly know that metals are good thermal conductors as well, right? Let's discuss about that thing, how to explain the thermal conductivity with the use of this model, right? So now I am supposed to explain you the thermal conductivity, which can be seen with the metals. Thermal conductivity. Thermal conductivity, right? So when it comes to thermal conductivity, what this means, heat should be conducted. So let's think of how the heat is conducted from one place to another place. See, if you have to heat, if you have to apply heat, some heat at this place, if this is a metal, let's think this is as a metal. If you apply some heat from this to this place, right, we would observe that heat will be transferred to this corner as well. If you apply some heat from this place, let's just think of some kind of heat, right, applying here. So that heat will be definitely transferred to this corner as well, right? Let's discuss how that happens. Right? How the heat will be transferred from one place to another place, right? Okay. When it comes to heat, right? Actually, it is known as the right, the kinetic energy of particles. Right? We will discuss that thing in the fourth lesson in your A levels. The fourth lesson, we will discuss this more. Anyway, heat is referred to as the temperature. The temperature is referred to as the kinetic energy of particles. Right? There's an equation in the fourth lesson like this. The average kinetic energy will be given by, right, 3/3 RT, right? So this is a constant, this is kind of a constant. So one can say, right, this is a constant, 3OT is a constant and R is another constant. So one can say when the temperature is high, the kinetic energy is high, or the kinetic energy is high, temperature is high. So temperature means the kinetic energy of particles. So if the kinetic energies of the particles are high, so if the particles are highly moving, right, that means the temperature is high. Right? This equation is there with the fourth lesson, right? Okay, that is the idea, right? That is the molecular level picture, molecular level idea of the heat or the temperature. Temperature means the kinetic energy. Right? So thermal conductivity means transferring the heat from this place to another place, or transferring the temperature from this place to another place. And that is what is meant by thermal conductivity, right? So on the other hand, temperature is the kinetic energy of particles. See what will happen. See how the heat or the temperature will be transferred from one place to another place by metals. Let's try to explain that scenario with the use of the truth Lorentz model. See, this is what happens, right? So if you have to heat from this corner, if you heat the metal from this corner, then this matter particle, this cation, will absorb that heat energy, and increase its kinetic energy. If you are to light up some candle or something here, right? If you are to light up some candle or something here, right, from here, right? So that energy, that thermal energy will be absorbed by this particle, and it will increase its kinetic energy. The thermal energy absorbed by this particle will increase its kinetic energy. That is what we say as that is what we feel as the increase of the temperature at this point. When you're supplying some energy here, heat energy, it will absorb, that heat energy will be absorbed by this cation, then it will vibrate, it will increase its kinetic energy. That means it will vibrate, right? That is the reason for increasement of the temperature. The reason for the increasement of temperature of that at this point, right? So when this guy is vibrating, it will collide with the nearest particle. It will collide with the nearest particle because this metallic bonding is kind of a strong bond, so the particles are very closely bound. As the metallic bond is referred to as a strong bond, right? A strong primary bond. The particles are closely packed, right? Closely packed solids. These are solids. So when this guy is vibrating, that will collide with the nearest adjacent cation. So the kinetic energy of this thing will transfer to here. So when that guy collide with the adjacent cation, right, it will also start to move, right? It will also start to vibrate. The kinetic energy of this thing will transfer to here. It will also vibrate. That means its kinetic energy also increases. That means the temperature goes to this point. Temperature of this point will increase. So temperature gradually going towards here. So when this guy vibrates, it will collide with the other particle, right? So that guy's kinetic energy will increase, right? That guy's kinetic energy will be ultimately increased, right? That means the temperature of this point will increase. Kinetic energy means the temperature. Kinetic energy means the temperature, right? So that is how the heat or the temperature will be transferred from this place to this place with the use of this structure, right? That is how we are explaining the transfer of heat or the thermal conductivity with the use of Drude-Lorentz model, right? So you can write like this. So thermal conductivity is due to because of presence of metal cations, right? Because of presence of metal cations, right? Heat supplied to one end can be transferred to the other end. Right, using the vibrations of metal cations. That way you can transfer the heat. Right? So even the electrons will participate in transferring heat, and this is how the metal cations are helpful to transfer the heat. Right? Both the electrons and metal cations both will contribute for the transfer of heat from one place to the other place, temperature, right? So basically this is how the metal cations will be helpful, right? So in your note you may have to do some changes here. It is said only about the electrons, but we'll include the right metal things here as well. So you can do the changes. It says because of presence of mobile electrons, that is there, and right there here there this thing as well, and due to the vibrations of metal cations, because of presence of mobile electrons and due to the vibrations of metal cations, that is okay. Then the things are there clearly. Heat supplied at one end can be transferred to other end easily. Write like that. Just remove the conductivity and just write heat supplied at one end can be transferred to other end easily. Right? So that is how the thermal conductivity is done by the metals. That is the explanation with the use of the Drude-Lorentz model. Right now? Okay. So let's discuss about more physical properties of metals. Right? Third thing. The third property we are going to discuss. Third property which we can see with the metals. That is about the hardness and the melting points. Hardness and the melting points. First, discuss about the hardness. Hardness. These are metallic lattice now. Right. Okay, let's discuss about the hardness stuff. Okay, this is right. So, number 3, hardness. Hardness and melting points. Lamai, hardness. Hardness means what? It is like this, no? Let's come up with a clear picture about this property, the hardness. Hardness means, right? Hardness means actually it's like this, no? So if you are with a material like this, right? If it is very hard to, right, cut the stuff into two, if it is very hard to cut the stuff into two, then we say such a material is kind of a hard material. If it is very hard to cut the material into two, right, we say such a material is kind of a hard material. If it is very easy to cut the material into two, then we say such a material as we refer to such a material as a soft material, right? It is what the hardness of means when it comes to materials, right? If your material is easy to cut to halves, from here as well, if it is easy to cut, right, then it is referred to as a soft material. If it is hard to cut into two pieces, right, then those materials are referred to as hard material, right? So basically, this hard soft nature will depend on right, the metallic bonding strength. Think of this. So if you are supposed to break this or cut this material from here. So if the metallic bonding between the atoms of that space, if the metallic bonding of the atoms of that space is strong, if the metallic bonding of the atoms at that space is strong like this, very strong, then it is very hard to cut this thing into two, no? If the metallic bonding between the two atoms is very strong, then it is very hard to put them apart from each other. So that if the metallic bonding is strong, we consider such a material as a hard material. So if the metallic bonding between the particles are very weak, like this, very weak, then it is very easy to cut into two pieces. So when the metallic bonding between the particles masses is weak, those are referred to as soft material. So the materials are referred to as hard and soft actually due to the strengths of their metallic bonding. If we are considering about the metals are referred to as hard and soft because actually that thing varies due to the strength of their metallic bonding, right? That is the idea, right? So one can say when the metallic bonding strength is high, the hardness is high. So one can say when the metallic bonding strength is high, one can say the hardness of your metal is high. right? On the other hand, right, when the metallic bonding strength is high, your melting points are also going to be high. Your melting points are also going to be high. Let's discuss about that thing. Let's discuss about that thing as well, right? So, what is referred to as the melting point? What is referred to as the melting point? Last day also we had discussed about this thing when we are discussing about the strength of the ionic bond, right? Let's quickly grab that idea again, right? Melting point. Melting point is actually the temperature you need to supply to melt a substance. That means to convert your solid into a liquid. The temperature you need to supply to convert your solid into a liquid. That is what referred to as the melting point, right? When converting a solid to a liquid, what happens actually? In a molecular level, what happens? When converting a solid to a liquid, in the molecular level, what happens is actually particles would get apart from each other. In a solid, the particles are very closely bound. When it comes to a liquid, the particles are a bit apart from each other. So when converting a solid to a liquid, what you do is actually what the supplied heat, what it does is actually they are used to put the particles apart from each other, right? That is what we are supposed to do when uh, you are doing kind of a melting, right? Okay, so the melting point means the temperature you need to supply, the temperature or the heat energy you need to supply to put the particles apart from each other. That is the simplest idea, right? Melting points means the temperature or the heat energy you need to supply to put the particles apart from each other. That is what happens when a solid is converted into a liquid. That is what we meant by the melting, right? So if the bond between the two particles, if the bond between the two particles is strong, is bond which sticks the particles together is strong, then you need to supply greater energy, greater heat energy to put them apart by breaking that bond. That means high temperatures are needed to melt your substance. That means your melting points will be high if the strength of the bond between the particles is high, right? When it comes to metals, the bond between the particles is actually the metallic bonding. When it comes to metals, the bonds between the two particles are referred to as metallic bondings, metallic bonds. So if the metallic bond strength is high, that means your particles are strongly bound to put them apart from each other, to liquidize them. That means to put them apart from each other, you need to supply high amount of heat energy so that the high amount of temperature should be needed. That means when the metallic bonding strength is strong, high, that means the melting points will be high. Need to supply greater temperature, melting points will be high, right? So that is the idea. So when the metallic bonding strength is high, hardness high, as well as the melting points are high. Melting points of your metals are high. This is the theory you should know. So metallic bonding strength as well as the hardness both depends on the hardness as well as the melting points both depends on the metallic bonding strength among the metal cations in your metals, right? Now that is the idea, right? Let's compare few situations, some examples for hardness variation as well as melting point variation, right? First let's compare two situations. Let's compare two metals, right? Let's consider which guy is with a greater hardness and which is with a smaller hardness, right? Some soft nature, right? So first consideration. So let's compare two guys. sodium and some other metal, iron, sodium and iron. Actual lamai, we know that sodium is referred to as a soft metal. Even in your small ages, we have learned that the sodium is a soft metal. You can even cut a piece of sodium with the use of a knife. With the use of a knife, even you can cut a piece of sodium very easily. Sodium is referred to as a soft metal, while iron is referred to as a hard metal, right? Sodium is referred to as a soft metal, while iron is referred to as a hard metal, right? Let's try to explain why it is so. Let's try to explain why the sodium is considered as a soft metal, or why you observe sodium as a soft metal and why you observe iron as a hard metal, right? Let's try to explain the two observations, right? Sodium is a soft metal, while Fe, the iron, is a hard metal. Right? Let's discuss how it happens. Right? When it comes to sodium, right? Its configuration is this, no? Neon and 3s1. When it comes to iron, its configuration is argon and 4s2 3d6. This is 26th element, right? So here we would clearly see sodium releases only these 3s electrons to the sea of electrons. But the iron will release more than that. Not only the 4s electrons, but also some of the 3d electrons will be removed. So the electron C, the electrons released to electron C will be high with the iron compared to the sodium. Right? That is one thing. Right? That is some one factor which affects the strength, right? So more electrons will be released by the iron to the electron C compared to the sodium. So more electrons released to the electron C means you are with a greater metallic bonding strength with iron compared to sodium. Greater the metallic bonding strength, greater will be the hardness with the iron compared to sodium. Right? That is why we say sodium is a soft metal while the iron is kind of a strong or hard metal. Right? That is the idea. So let's write the points there in your note. Just complete the stuff. Sodium is a soft metal while Fe is a hard metal. Right? So these are the points. So you can come up with the electron configuration and then you can write, right, to the metallic lattice, sodium releases only the 3s electron, only one electron, right? One electron, while iron releases not only the two 4s electrons, but also some of 3d electrons. Because yet they are not achieving the Nobel gas configuration, right? So they can release more electrons, the iron. But here, after releasing the first electron, it touches the noble gas fission, so that it is not releasing the electrons furthermore, no? So that sodium releases only one electron to the electron C, but iron release more, right? Right, to the electron C, to the electron C, C of electrons. So you can write, so electrons released to the electron C is low in sodium and greater in iron. So metallic bonding strength is greater with the iron than in sodium, right? More the electrons are raised to electron C, metallic bonding strength will be high, right? So that one can say sodium is a soft metal, and while the iron is considered as a hard metal, all due to the metallic bonding strength. So hardness is low with sodium and high with iron, because greater the metallic bonding strength, greater will be the hardness, right? That is why the iron is with a greater hardness than the sodium, right? No? So these are the points you need to mention if they have asked a question to explain why the sodium is referred to as soft, why sodium is observed as a soft metal while the iron is can be observed as a hard metal, right? Okay, so that's it. Here's some comparison with the use of metallic bonding structure, the Drude-Lorentz model. Right now, just complete the stuff here. Right. Let's discuss about another example. Let's discuss another example here. Right. Let's discuss an example for melting points. Right. Some example for melting points. Right. Melting points. So melting point variation of sodium, magnesium and aluminium actually are given like this, are as follows. Right? The melting points are like this. So let's see. So we have the metal here and the melting point in Celsius for the sodium, magnesium and for the aluminium. Actually the values are sodium is with 98, 650, 660. Right? Let's try to explain this stuff. Right? Actually, when going from sodium to magnesium, see what will happen. When going from sodium to magnesium, right? Number of electrons to electron C will increase. Sodium releases only one electron, forming Na plus ion. Magnesium releases only 2 electrons, forming magnesium 2 plus ion. And aluminum releases 3 electrons to form the aluminum 3 plus ion, right? So from here to here, sodium to aluminium, right? One can say, right, number of electrons released to the number of electrons released to electron C will be increased from sodium to magnesium to aluminium. Then the size of the cations also decrease from sodium to aluminium, going from sodium to aluminium. Size or radius of metal cations will be like this. Na plus is larger than magnesium 2 plus, which is larger than aluminium 3 plus. So those are isolated species. When the charge of the isolated species increase, positive charge increase, the size becomes smaller, right? When more electrons are released to the electron C, and when the radius is smaller, then what will happen? Then your metallic bonding strength will increase. When the more electrons are released to electron C, that is what happens to the aluminium. And when your cation is smaller, the size, right, your metallic bonding strength will be the highest, right? So that we can write, so metallic bonding strength will vary like sodium is with the least, then the magnesium, and greatest with the aluminium. Sorry, sodium is with the least, then the magnesium, and greatest is with the aluminium. Metallic bonding strength. So that when the metallic bonding strength is high, right, your melting points will be high. So melting point variation will be like sodium is carrying the smallest, and magnesium is high, and aluminium is coming up with the highest, with the greatest metallic bonding strength, right? So that is how we are supposed to explain this kind of observation, right? Okay, right. So you can complete the note here, right? So for the metallic bonding, major two facts we have to think of is number of electrons related to electron C, and the radius or the size of the metal cation. Those are the major two facts which governs the metallic bonding strength, right? So the ionic nature could be used with the D block guys, not when comparing the S block guys, S or P block cations, metals, right? Okay, that is about the metallic bonding. Right. Let's discuss about another example for metallic bonding. Right? Okay. So there could be a question like this. See. Right, one can ask a question like this, right? Right. Part C. Another question. Let's write something, some comparison with the use of that ionic nature. So this is another observation. Right? Zinc is with the zinc is with the smallest melting point. Zinc is with the smallest melting point among (3D) elements. Zinc is with the smallest melting point among 3D elements. That is kind of observation, right? Let's discuss about the reasons for this thing. Zinc is with the smallest melting point among 3D elements. The reason is this, right? So zinc, when it comes to zinc, its configuration is, right, argon and 4s2 3d10. Zinc is your 30th element. So it is a stable configuration. So we can write zinc, right? Zinc is with a stable electron configuration. Stable electron configuration. Zinc is with a stable electron configuration where the SN, OSN 3D subshells are completely filled. So that we can say the ionic nature matters here. The ionization energy of zinc is the greatest among 3D elements, 3D row elements. So when your electron configuration is with a very stable configuration like this, completely filled. When the subshells are completely filled, that is a very stable configuration. That means it is not keen to release electrons to the electron C. So the ionization energy of the zinc is the greatest among 3D elements. So least number of electrons will be released by zinc. So the least number of electrons will be released to the electron C by zinc. Compared to other 3D elements. So metallic bonding strength is least with zinc compared to the other 3D elements. So the melting point will be the least compared to the other 3D elements. Right now? So that is the idea. So these are the points you should write. Right? If they have asked you to explain this kind of stuff. you have to start with the electron configuration, and with the use of that you can explain the ionic nature, right? Now, so this is the idea, right? Actually, this is all you should know about the metallic bonding, right? This is the last primary bond, right? This is the decision of the last primary bond, right? Now we have completed the decision about the covalent bond, ionic bond, as well as the metallic bond now, right? So you can complete the note here, right? That is the end. This is the end of the discussion for the metallic bond.